So let's move on straight to Nina, who will tell us where the food in the future will come in a hotter, more crowded world.
Okay, well, I was told I had 8 minutes, not 5 minutes. I've been asked to answer the following questions. Can we double the food supply and still shrink the ecological footprint of agriculture? And do we need to double the food supply? I think I'll be lucky to do justice to the first in my allotted 8 minutes. You're all familiar with the population projections. It looks like we'll be 9 to 10 billion by mid-century. But since the amount of arable land on the planet hasn't increased in more than half a century, there's less and less of it per person. Irrigated agriculture is the most productive agriculture in many places, but it's basically living on borrowed time. Aquifers around the world are being exhausted at an ever-accelerating pace. Sorry about the old slide. Then there's climate change. We are rapidly moving out of the temperate range in which we domesticated our current water-inefficient, temperate staple crops. To make this real, I draw your attention to this little X, which was the very hot summer of 2003 in Europe. We all remember the 30 to 50,000 heat fatalities, but who remembers that crop yields decreased by a quarter to as much as a third? This will be an average summer in not too many decades, and an anomalously cold summer by the end of the century. So, can we expand the food supply using less water in a warming climate while reducing agriculture's ecological footprint using less land? A pretty tall order. How? Well, we need modern technology and modern science everywhere and in every aspect of agriculture, and we need to professionalize farming as it has been professionalized in the developing world. We need to redesign agriculture as an integrated system that is land, water, nutrients, and energy. And we need to farm in cities, on rooftops, for cooling, heat management, and to decrease transportation costs. And we need to think out of the box. New technology, new crops, new land, new water sources. Let me just give you some examples of how things have evolved and continue to evolve. Here's the progression of innovation in irrigation technology from spray to low energy, precision application, to drip irrigation, to subsurface drip irrigation that can deliver both water and nutrients directly to the roots. That's called fertigation. It uses less water and it causes less nutrient pollution. Hydroponic agriculture in greenhouses is extremely productive, cuts down on toxic chemicals, and is water efficient. This greenhouse produces about 100 kilograms of tomatoes per square meter per year. This is easily 10 times and sometimes as much as 30 times the yield in open fields. Here's a hydroponic lettuce growing facility in Canada. It recycles its water, works year-round, and the yields are easily 5 to 10 times as much as in open fields. This is a hydroponic lettuce facility like the last one I showed you, but instead of using chemical fertilizers, it grows high-value trout in the tanks and uses the nutrient-rich water from the fish tanks to provide fertilizer for the lettuce. This system is a very old form of organic farming with a new name, aquaponics. It conserves on water and uses the nutrient inputs to the fish much more efficiently. Hydroponics and aquaponics can be done in the city. Indeed, there are efficiencies in energy and water use as well as savings in transportation costs to be gained. Today, as you heard, almost half of the fish and shellfish we eat is produced through aquaculture, some using fresh water, some using seawater. Causes pollution today, it doesn't have to. This is an aerial view of the National Prawn Company in Saudi Arabia, near where I am working now as a professor at the King Abdullah University of Science and Technology. This is actually one of the most advanced facilities in the world. It produces 20,000 tons of shrimp annually. Each tiny square in that pattern which I hope you can see, is a 10-hectare pond. Now, fish and shellfish are amongst the most efficient sources of animal protein. It takes about 1/10 as much feed to produce a kilo of shrimp as a kilo of beef. The challenge is to make better use of the nutrients that are currently discarded in such seawater farms. That requires plants that can grow in salt water. These exist, and of course there's marine algae. The land plants that can grow on salt water are called halophytes, but they've never been domesticated. So what's domestication? Domestication is genetic modification. This is teosinte, the wild relative of our familiar corn plant. The transformation from the inedible seeds of teosinte, shown on the left, to recognizable corn was done by people many thousands of years ago. But the next leap in corn productivity happened in the 20th century, based on the exploitation of hybrid vigor, first described by Charles Darwin. The molecular revolution of the 20th century opened a new avenue of crop protection and improvement through biotechnology. On the left, you see the damage done by the European corn borer. On the right, you see an ear of corn expressing a protein that is toxic to larvae of insects, but not toxic to animals or to us. The introduction of this GM corn and other crops with the same trait has markedly reduced the need for using toxic pesticides to kill the insects. This biological approach has had another benefit in that the fungi that follow the insects into the plants produce toxic and carcinogenic compounds called mycotoxins. No insect holes, no fungi, no mycotoxins. Now, despite the urban myths that continue to proliferate about the dangers of GMOs, GM technology isn't dangerous. The European Union alone has invested more than 300 million euros in research on the biosafety of GMOs. As you can see in this quotation, which I'll read to you, you don't have to compete with what I'm saying. The main conclusion to be drawn from the efforts of more than 130 research projects covering a period of more than 25 years of research and involving more than 500 independent research groups is that biotechnology, in particular GMOs, are not per se more risky than conventional plant breeding technologies. Every credible scientific body that has examined the evidence has come to the same conclusion. Fortunately, there's good news as well. Despite continuing controversies and anti-GM activism, crop acreage has increased rapidly worldwide. In 2011, GM crops were grown in 29 countries on 160 million hectares. More importantly, 90% of the 16.7 million farmers growing biotech crops are smallholder, resource-poor farmers. And yet, after all of these years, and it has been decades, and given all of the promise of molecular methods, we have virtually no GM crops other than cotton, corn, canola, and soybeans. Even the long-awaited golden rice is not yet available to farmers. Insect-resistant eggplant is stuck in regulatory limbo, as are other crops such as the late blight-resistant potato. That's the disease that caused the Irish potato famine. And animals such as rapidly growing salmon are not still available to farmers. So in summary, it's my view that there's plenty of room for increasing agricultural productivity. We can feed 10 billion people, but will we? Progress on slowing climate change and improving water management is glacial. Governments have been underinvesting in agricultural research for decades. Private investment in primary agriculture is not popular, so it's very hard to round up the capital needed to bring high-tech agriculture to the less developed world where land is still plentiful and yields are very low. And we continue to over-regulate or even completely prevent the use of most modern methods of crop improvement. Only the big commodity crops can support, and only the big biotech companies can afford to bring a GM crop to market. It costs about $35 million per crop just to comply with regulatory requirements. Now, none of these are scientific or technical problems. They're policy, regulatory, financial, and social problems. Will we solve them? I don't know. Thank you.